Hello, today I'll be talking about gas loss in this video. This is the second part of my previous video where I spoke about the properties of gases. Today I will be talking about gas loss. So, what are the gas laws? These were uh, explained to talk about gases, and there are mainly three laws which are considered as gas laws. The first one is Boyle's law, and the next one is Charles' law, and the third one is GAY-LUSSAC'S law. If you combine these three laws, we get the combined gas law. So why only these three laws are considered as gas laws? Because these are the three laws which show the relationship between the pressure, volume, and temperature of the gases. So when we studied about the properties of gases, we said that the pressure or the collisions are impacted by volume and temperature. So these are the three laws which state the relationship between pressure, volume, and temperature. So we will be studying each and every law in detail. So first thing, who is Boyle? So Robert Boyle was the first person in the 16th century to study the relationship between the pressure and volume in a systemic way. Because people back then knew that as there is some relationship between pressure and volume. If you are increasing the pressure, the volume is decreasing, but they didn't know what exactly was going on. So Robert Boyle was the first person to publish his law in 1662. What did he stated? That at constant temperature, the volume of gas is inversely proportional to the pressure. So, which means at any constant temperature, if the pressure increases, the volume decreases, and if the volume increases, the pressure decreases. And he gave this law in a form of an equation, which is PV is equal to constant, means the pressure and volume as they are inversely proportional. You can say that P1 times V1 is equal to P2 times V2. So this is the equation which you usually use to solve the problems when they are given based on the Boyle's law. So okay, we studied this Boyle's law. Are we really applying in the real life? Are there any examples for it? Yes, they are. First, one of the best examples is our breathing. So when we inhale, we no need to put on pressure. But when we exhale, we have to put little pressure. So when you are exhaling, the volume of the lungs or the volume of the air in the lungs is decreasing. When you are inhaling, the volume is increasing. So the pressure decreases, the volume increases. Okay, this breathing thing looks little complicated. Can we have something in simple? Well, this is the easiest and the simplest application which we do in everyday life. If you are using a syringe, if you pull the plunger, the volume increases. But how to decrease the volume of this air present in here? Just push the plunger. You have to apply pressure, then the volume decreases. Okay, fine. Syringes, we are high school, we never used syringes, probably we just go for an injection. So how about balloons? You must be popping balloons. So when you apply pressure, the volume inside the balloon is going to decrease. So applying pressure, the pressure increases, the volume inside the balloons decreases. Even soda cans or the bottles, they have air here which are under pressure. So when you open the pressure or open the cap, the volume of the gas increases and the pressure decreases. So these are the best real-time examples of Boyle's law in everyday life. So how are we going to graph it? Looks like this. So if you plot a graph pressure on y-axis and volume on x-axis, you can see that it is decreasing. Here's, if you see, it's highly pressurized. So the volume is less, the pressure is high. Here you have increased the volume a little bit, so the pressure decreased. Here you increase the volume a lot and the pressure decreased a lot. So this is the best interpreting graph of Boyle's law. Now, what is Charles' law? Well, Charles' law was first published by Gay-Lussac, and he credited Charles, a balloonist, for his unpublished work from 1780s, and he named it as Charles' law. Jacob Charles was the first person to actually fly in the hot air balloon. He was a balloonist, so he was always trying and experimenting with balloons, and but his work was never published. He got into the hot air balloon, he heated up the helium balloons, and he was able to float. But he never published, oh, this is a law, because he's a balloonist. He never thought about science in that way. So it was Gay-Lussac. He was the one who was able to publish the law, but he named it after Charles. So the Charles law states that at constant pressure, if you increase the volume, the temperature is going to increase. If you increase the temperature, volume is going to increase. They are directly proportional. And this gives a relationship between the volume and temperature, but at constant pressure. So when in the hot air balloon, when you apply a lot of heat, the volume of the balloon is going to increase and it's going to float. So that is how this Charles law was derived. So it is given by the equation V by T is equal to constant, which is V1 by T1 is equal to V2 by T2. So this is Charles law. Now, what are the real-time examples? So here are some real-time examples. If we look at Charles' law, real examples, hot air balloon as I was talking about, look at the bread. Bread, when it is in the batter form, when you put it in the oven, has a lesser volume. But once it starts heating, the yeast are going to expand and they're going to expand the bread. It becomes fluffy and the volume increases. Another example is your ping pong ball. When you have a dent in it, put it in the hot water. The dent is gonna go away. The volume is going to increase. How about the tires? Did you ever see that the tires at colder temperatures or in the winter season, they always deflate, and you have to always put in air into the tires in winter season because of the temperature. The temperature decreases, the volume also decreases. Even the float, if you ever go for swimming in the floats, if the water is too cold, it's going to shrink. The floats are going to shrink. And if the water is at room temperature or warmer, especially in summer, you can see them inflating. They don't shrink that easily. So these are one of the best examples for our real life applications of Charles. And how does the graph is going to look? So if you increase the temperature, the volume is also increasing. If you see here, the graph is just linear. So this is how the graph for the Charles law is going to look. So what about Gay? So Gay-Lussac's law, this is his personal law or his personal discovery. You can say that he published the relationship between the pressure and temperature at constant volume. But when did he discover? While building an air thermometer. He had the volume of the air constant, but when the pressure was increasing, the temperature was also raising. And when the temperature raised or decreased, the pressure decreased. So he was able to give the relationship between 1800 and 1802 that the pressure is directly proportional to the temperature at constant volume. And this relationship is given by the equation P by T is equal to constant, or P1 by T1 is equal to P2 by T2. As I'm talking about the real-time examples, Gay-Lussac's law, as what is the Gay-Lussac's law? It's at constant volume, right? So one of the best examples is pressure cooker. if you ever cook food in the pressure cooker, the volume or the food you put in here is going to remain constant. You're not going to open the cooker and put some more stuff here. So at constant volume, if you increase the temperature or you heat the food, the pressure is going to increase. You hear the whistles or the sound. So the pressure need to be released out. So as you increase the temperature, the pressure increases. Or the tires. So what is going to, in the tires, if they're having constant volume of gas, what is going to happen to the tires at high temperatures? The pressure is also going to increase and they're going to burst. And one more example is aerosol cans. If you use perfumes or spray paints, whatever aerosol cans you use, they always say to keep them away from high temperatures. Why? Because the aerosol cans at high temperatures are gonna burst because of the increased pressure. So these are the best examples of applications of Gay-Lussac's law. But how is the graph? It is going to look similar to Charles' law. But here it's at absolute temperature and the pressure. The temperature is on the x-axis and the pressure is on the y-axis because it's at constant volume and it's a linear graph. And when you combine laws, Boyle's law, Charles' law, and Gay-Lussac's law, you get the combined gas law, which gives the relationship between pressure, volume, and temperature. And it can be given by the equation P1 V1 by T1 is equal to P2 V2 by T2. You have a lot of problems on this combined gas law. So this is about the combined gas law. You're giving the relationship between the pressure, volume, and temperature. So combined gas law describes the relationship, as I mentioned, in an enclosed gas. So here you can see we try to plot all the temperature, pressure, and volume in the same graph, and you can see how they're gonna look. So this is about the gas laws. So here are the key equations I included. So Boyle's law, Charles' law, Gay-Lussac's law, and combined gas law. So these three gas laws are very important, and when you combine these three gas laws, you get the combined gas law. So these are the questions, or these are the equations which are used to solve a lot of problems. I'm not discussing about the problems in this video, I'm just discussing the concepts. In the next video, I'm going to talk about ideal gas law. We came from gas law, what are the properties of gas laws, and then we spoke about the combined gas law, and next we are going to jump to ideal gas law. In my next video, I'm going to talk about ideal gas law. For now, this is it.